Okay, so I didn't do something yesterday when I finished the chapter, but let's revisit this. So we looked at this figure, and I said that on Earth, as you go from the equator to higher latitudes, the relative distance, the distance from the axis of rotation decreases. If you remember, a cosine phi. Cosine phi keeps going to zero as you go to the pole, right? That does lead to angular momentum conservation problems and instabilities, as we will see later on. But the amplification of this was actually shown in a bathtub by Perrot back in 1859. Okay, so he did the Foucault pendulum equivalent in the bathtub. Basically, we will see that if you set up a tank with water and just leave it alone for a day or two, it's not rotating, it's just sitting, right? It should acquire the rotation of the local F. Okay, at any latitude you are, we said F is omega sine phi, so it should acquire the omega of the Earth, and then the experiment can be set up to see how the natural omega acquired from the Earth's rotation in the tank is amplified when you change R. Okay, so the simple equations we will see in the tank are V1 equals R1 omega Earth at the edge of the tank, and it has an angular momentum of V1 R1, the radius of the tank, and then as you go inside towards this drain, right, so the tank is just sitting for a day, all the water is simply sitting, but it is slowly acquired Earth's rotation. How do we know that? Basically, if you unplug this drain in the middle, okay, so this is the setup. You have a tank set up, just sitting quietly, doing nothing to it, and you have a drain in the middle. So the pressure here will be less than the atmospheric pressure when you unplug it, so the water will get sucked in and it'll start flowing. Obviously, very tricky because the outer edge V1 has to be in fact quite small to avoid frictional effects that you would see in a regular bathtub or a flush and so on. So Perrot did that. So here's the MIT setup, and John and Alan warn you that this is a very tricky experiment and you may have to do it many times, which means you have to wait 2 days, do it again, or day and do it again, day and do it again, and so on. Okay, so that's where this amplification comes from. Okay, so R1 or R0 squared omega Earth sine phi, where omega Earth sine phi is the local F that the water particles acquire just by sitting on Earth. So we all experience it, but obviously we don't notice it. But in a tank you can recreate it. So what happens here is the water parcels, as they start moving in, they will begin to make a circle towards the middle, and the rotation rate itself is amplified by where you are with respect to the outer edge. So you get R1 or R0 squared. Okay, this is Perrot's experiment. This is essentially the equivalent of Foucault pendulum, right? Foucault looked at the pendulum and said it just doesn't swing, but it's making these circles that we saw the animation. Because of Earth's rotation, this is the same thing in a water tank. Okay, except there it was just going around. Here we are amplifying the rotation itself. Remember the other experiment we had seen by changing the rotation rate from 5 RPM to 10 RPM to see that the rotation and the tangential velocity going in increases as the R0 decreases, as R decreases. Okay, so I wanted to make sure that we didn't miss this great experiment that Perrot had done to show that the theory actually works, even though the lab experiment is hard to do. Lab experiments obviously always confirm that whatever math we are deriving actually works. The physics is actually real, right? So that's the cuteness of these fluid experiments.